Alright, and back on. Let's see if this actually updates. Alright, back. I am now warmed back up and had something to eat. So let's get back to work. So the microprocessor's now on sheet 2. And another thing that we're going to need is some more power conditioning. So this 48 volts is going to have to get turned into so the teensy needs 3.3 volts. There's a feedback circuit for the buck controller that probably will need 5 volts, and 5 volts probably for a USB or something else. If we wanted to do serial or GPIB, I think we're going to need 12 volts in order to get that done, as well as any relays or anything else that we might need. So we've got a few voltages that we are going to need to split out of this 48 before it gets to here. It's beefy enough to do it, we can do it pretty easily. So that is going to be power rails. Control power. Now remember, these voltages are not actually going to be spat out here. They're what's going to be running these guys. And any other control or other stuff that we're doing. And then one other thing that we're going to need here in this control sense area, or in the current sense area, is we're going to need something that feeds back to the microcontroller. So that the microcontroller actually knows what the heck we're doing. Because it will not be happy if it doesn't know information coming back on what voltage is what, or what's going on and what's happening. So this is going to be voltage and the whole point of that guy is to give the microcontroller the information that it needs to go ahead and clamp the output, or to change what this voltage needs to be, or otherwise impress upon our power supply what he needs to do. So let's go ahead and figure out these control power, because that's going to be easy. So we've got our micro going in there, and we're going to be able to go ahead and feed him. But we need to make sure that we've got good power to him. So, description. Alright, so the first things first is we have 48 volts to play with, and we need to be able to find a way of making 3.3 volts. That's going to be our most important thing. So we go over to the place where I like to cheat things, DigiKey, because they've got a real decent way of being able to find some of these parts easier, and they also have all the data sheets. So instead of going from, and you can do this on Mauser as well, I believe Newark has some similar functions or anything. This is just the one that I'm more familiar with. I've done a lot more ordering from them for small numbers of components for prototyping and everything else. They're decent. But there's also Mauser.com, there's also Newark.com, there's also a few others. So, and what we're going to need is, let me see. So if we go to products, and I'll actually bring up the whole list of everything. And we're just looking for integrated circuits, PMIC, and we have voltage reference, regulator, DC switching controllers, DC switching regulators. So we actually want a regulator. We don't want a controller. And we do not want to have anything that's linear and switching, or just straight regulators. Because we don't want to be, when you have a high input voltage that's a lot higher than what your output voltage is going to be, even if you're only using, let's say, 100 milliamps. Well, going from 48 volts to 5 volts means that you're skipping about 43 volts. So anything that's being used by the 5 volts, current-wise, is also going to have to be thrown away by the part on a standard regulator. So we want to use a switch. So we're looking for, in stock, will tell us that we've got something. And they've got step up, step down, step down, step down, whatever. We're not caring about that. Topology, don't care. Number of outputs, 1, 1, or 2 is fine. Voltage input minimum. Actually, we don't care about that as much. The maximum voltage input, since we're using a 48 volt supply, we're going to go ahead and just say everything that many's. Apply filters. 10 of them in case we blow them up. Set to price. And then this guy, input 8 to 50 volts. And see this? Now the output current means that he can handle an awful lot. The output voltage from 0.8 to 24 volts. This means that this is going to be another, basically the same kind of guy that we're using on the other one. He's also the cheapest one on here, which is good. Probably do the job. I'd rather have something, that price doesn't care. So we're just looking at something that's going to be able to handle it. Looks like these are all about the same. 500 milliamps is going to be more than enough. This guy's just a little SOT23, so this might be good. So let's look at him. So we'll just give him a look. Input voltage range up to 50 volts. Output 2 to 24, good. Integrated N-channel buck switch. Up to 1.2 amp current at 3.3 and 5 volts V out, VN greater than 12. So as long as the VN is greater than 12, we can have a voltage output of 5 volts. That's perfect for what we need. We need 3.3. Up to 0.08 amps at 12 volt. So this might actually be all three of our guys. We might just put 3 of these on the same board. Easy enough to do. 6 lead SOT23. This is a tiny little package. It's meant for industrial input, DC to DC conversion. So this might actually be a good one to do. We've got in, we've got enable. So the enable pin is going to be fine. We're not really going to be turning this on and off, but if we have other ones of these, we can actually control those on the micro as well. So here's the gotcha. So you see this where it says typical application. So this is VN and then the boost. We've got a diode here. We've got an optional capacitor there. 2 by 10 microfarad. 22 microhenry inductor. So this all actually seems bog standard. So for this little tiny device, we're going to go ahead and probably use these because it looks like the input and the output capacitors and everything else look pretty darn simple. Schottky diode, of course. Anything that goes way out transient, you don't want that spewing across, or if something goes really wrong. 22 microhenry inductor, those things are tiny. Not really worried about the cost on those. So this actually looks like it would be cost effective. On some other ones you might have it where they're like, yeah, well, you need a big capacitor, or you need tantalum, or you need this or that. So let's see what this guy says that he needs. From typical output, it looks like, or typical, looks like he's fine. Output efficiency, and this is going to be real typical of any sort of buck switch, mostly because it uses a certain amount of energy regardless of what it's doing. So as soon as you're drawing more current, it's just going to be one of those laws of averages. But out here, we're starting to get into the, so voltage in 48 volts, it's not as efficient. We're fine. We've got so much overhead, it's extra, it's not even worth worried about. So 5 volt out, efficiencies, whatever. At 3.3 volts, not so good. We're not drawing a lot of current on that. We're not going to do a 24 volt out. So looks like we're just going to be fine with this guy. There's nothing too silly that we need to worry about. Shutdown current versus, yeah, we're not going to be throwing a lot of current through this guy. And we're not going to be shutting him down and still running him for anything, so that's fine. Switching frequencies, stable. Alright, so load transients and stuff. This is more information than we need right now for just grabbing a little chip that's just going to get a stable voltage and just spit out something we need. So switch node is connected internally to the NMOS switch and externally to the blah. So the external Schottky diode should be connected close to that. Okay, good enough. Boost pin supply for floating the high side driver used to turn the integrated on and off is connected to the boost pin. Fair enough. So what I want to see, alright, step down or buck converter. Yes, that's exactly what we want. Average chop down. Okay. Yep, that's exactly what it's doing. Okay, adjustable output voltage calculations. So this is the information that we're going to need in order to actually connect whatever resistances or whatnot to it in order to be able to get what we want out of it. So we'll go ahead and save that for later. Aha! This is what we need to know because continuous inductor current duty cycle features integrated slope compensation. Fair enough. All right. So this gives us a nice handy chart telling us how big our inductor needs to be in order for stuff to be roughly clean. Simple. Alright, 15 microhenry inductor, 3.3 volts out. So let's, just to make this easy, 15 and a 22. And capacitor selection. As with the input capacitor, X5R and X7R ceramic capacitors are well suited. This is great. This is good news. You don't have to use electrolytics in order to do this. This is going to save us a ton of cash because these chips, X5R and X7R ceramic capacitors, are incredibly cheap surface mount jobs. So this is going to take up very little space on our board. So perfect. So we're probably just going to go ahead and copy exactly what the typical application 3.3 and 5 volts is. So we're just going to go ahead and shamelessly copy this because this is perfect for what we need. These are bog standard surface mount capacitors. These resistor values are already found for us, so we know what we got over there. And then there's nothing going to be fancy about the inductor. So let's go ahead and plug this in. Alright, so first things first. This is the MCP16331. So let's see if we get lucky. Eagle! Microchip. And it's 16, microchip 1.5, PFC. Probably not. Voltage reference. Nope. Alright. So we go back to our library. New MCP. Oops, sorry. Oh, that's going to get a little annoying. There we go. MCP 16331. Create a new symbol, yes. That symbol is going to be, let's go ahead and zoom in, scroll, there we go. Because I do not want to have to prototype and solder with a surface mount paste under pad part, we're just going to use the little SOT23. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Properties. Alright. boost, visible pin, pin 2 is GND, visible pin, VFB, SW, VIN. Need to go back and fix the other one. And the enable. Easy. Name. Value. And there we go. Save. This part's going to be fun. So we're going to go ahead and new package. And SOT 23.6. Sure. Now, why am I building a new package for this? Well, because if you copy a package from an existing library, it makes a mess. So we're going to go ahead and open another copy of Eagle real quick. Libraries. And let me see. DC to DC converters. Packages. Nope. Diode discrete display, blah blah blah. Search. SOT 666, SOT 223, SOT 23R, SOT 23. Next. Aha! There we go. We found one. Reference packages.library. Alright. So we'll go ahead and open this one. So what library is this? Reference packages.lbr. Oh, that's right, duh. Package SOT. That one. Copy group. Paste. And that's magically going to be done for us. So let's make sure. Okay, that's pad 6. And that's pad 1, because sometimes you never know. So we're going to go ahead and now save that. We're going to open a new device for the MCP 16331. Yes, I want to create a new device. We're going to add our little guy there. Again, add the package. Prefix is going to be U. Value on. And connect. So, boost is pin 1. Enable is pin 4. Ground is pin 2. SW is pin 6. FB is 3. And VN is 5. OK. Variable voltage output switching buck converter. Good idea to always put a nice little description of what you've created so that when you go back later, you can find it. Alrighty then. So now we save. And we can go ahead and put you away. We can go back to you later. So now we're going to go ahead and add our new part to the schematic. Okay, power supply stream. And there is our MCP. And we know that we want at least 3 of them. Because remember, we wanted 12 volts, 5 volts, 3.3 volts. Okay. So 1N4148. So one of the things that I'm going to be doing on this is I'm going to make sure that every time I need a part, I'm going to go ahead and make a new part for the library, either copy it over or do something else. And the reason why for that is when I'm done with this, I want to be able to hand the schematic and the part library to somebody, and they're going to be able to go ahead and do their own layout or anything that they want to do with this. So having that option available means that I can save somebody some time and they can learn from this as well. So looking through the libraries, search, and it is saying 1N40 148. And we'll just see if it finds it, and if it does, we'll just copy it over. A piece at a time. We don't want to copy over the entire group from the library, because I want to keep the library for this build as clean as possible. And there we go. And it looks like it found just a through-hole diode. A big old thing. Huh. Let's see what we can do about that. So we'll go ahead and go back to DigiKey. And we already know this guy. So we're going to go back to the product index. And again, we're going to save this, save file, and then that way we've got that for later. So we need a 1N4148. Single. There are lots. There are surface mount. Surface mount is always better. Only because it's mostly smaller, you get the same thing, and quite frankly, they are cheaper. So, reverse voltage, any of those will be fine. Surface mount versus through hole, whatever. So let's see which ones you have in stock. All right. Heater. All right. So SOD 523 standard package. So let's do it that way. SOD 523. Thank you. And again, we're going to copy group, open the library we were working with, SOD 523. Paste. There we go. And then the other thing is that there is the line there, E. Nothing to it. Perfect. Alright, and I already saved that, and I've saved you. And then the only thing I need is a diode symbol. away. Oh, I didn't start over. There you go. Find a diode. NPN plus diode. Oh, come on. Be better than that. There we go. Open in library. Edit symbol. Select group. Go away. There we go. And symbol. Diode. Yes. And we have a diode. So this is going to be taking up a bit of time, but at least I'm getting it done. Save. Package. New. And this is going to be the 1N4148. Okay. Yes. Diode. Value prefix D. Connect. A to A, C to C. It's that easy. Save it. Go to sleep for now. And according to the thing, there's one there, there, there. One for each. Aren't you so lucky? Helps them I'm smart and kept that up. Thank you. Alright, select, flip, flip, flip. Nope. Alright, so 100 nanofarad boost cap. So C boost. How do we figure out that guy? Boost capacitor. As recommended, the boost capacitor maximum voltage is 5.5 volts, so a 6 volt or 10 volt rated capacitor. Okay, the boost capacitor is used to supply current for the internal high side drive circuitry. Okay. That's easy enough. So I just need to get a capacitor that's rated for the voltage, and X5R, X7R capacitors recommended 1 microfarad. Okay, good. That's gonna be with that. Yeah, this is not going to be expensive at all. But I really don't want to solder something that small. Okay, so let's make sure we've got our voltage rating good. They recommended 10 volts and up. X5R or X7R. In stock, apply filters. These are, because we're looking at 0.1 microfarad capacitors, we are probably going to have lots of these. Package case. 805 or 1206 will be just fine. Alright, so 0805, 50 volt maximum, 0.1 microfarad, and they are super cheap and really easy to get, so I'm not even going to worry about data sheets or anything on these. 0805 is bog standard, So this is going to be perfect for what we need, and we're just going to go ahead and use lots of them. So every capacitor we're going to use is going to be 0.1 microfarad. We'll just use the 50 volt, because if we use more of the same part, see this, the pricing, the more of the same part that we use, especially with these small ones, the cheaper they get. So buying 5 would be 50 cents. Buying 50 is also 50 cents. It's not until you get to 250 of these that it's getting close to $2 total. So if we just use the same part over and over and over again, you'll actually save yourself a lot of money. I mean, 1,000 of them is $4. It's not, this isn't too bad. So we're just going to make sure that we're going to copy that, and we're just going to put that onto, move you out of the way for a minute, and we'll just make sure that's the description that we put when we make our part, because when it actually will come out, when we do our bill of materials, which gets generated from the board that we make, it's actually going to have that description. We're going to be able to find this easily. So alright, so back to this. And that's going to be in resistor, because I remember exactly where that guy is. So let's just close some of this off. Resistor, here we go. Capacitor, US, packages. Do 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 do. Oh, 0805. So open in library. Copy group. Escape. And new package, C0805, OK, yes, paste, there we go. Yeah, I did get the message, I just didn't have the thing over. Ooh, I get a crown. I haven't done this before. It's shiny. I'm easily distracted. What was I doing? Right! A capacitor. Alright, let's go ahead and save you. Symbol. Cap. Yes. Now, the thing that's going to happen is that every time we add another kind of capacitor or something to this, we're going to keep adding it to cap. If we have to add a polarized capacitor, I'm going to go ahead and do a different schematic symbol for one that is actually polarized. And the reason for this is because some of them are, some of them aren't, but it's going to give us one thing where if we need a capacitor, we're going to have the different packages all available so that you can choose the different packages or the different individual things without having to go from part to part to part to part. So this keeps it all cleaner in the library. Alright, so once again we go back to U, and we're going to open the symbol for capacitor US. And select group, copy group, paste. And yes, if it seems like I'm saving a lot, I'm saving a lot. When you work on something and have it go completely on you after a while, you do that a lot. I've seen people where I work who haven't saved things in weeks. They're sad when the power goes out. So we're going to have a new device called capacitor. And again, same thing we're doing, because we are building a library from scratch while we're doing this. And we've only got one package that actually fits for this right now, so we'll just go ahead and use him. Prefix is C. Value is on. Connect. Good. I mean, you can't even tell in the real which end is front on these, so it doesn't matter at all. And we're done. Save. You go away. And again, back to our schematic. And this guy is going to use a bunch of these. So we're going to open capacitor. So we know for a fact that it's asking for 1, 2, 3, 4, 5, 6. 1, 2, 3. And then on the output, if I was smart, I would have left that up. It says that there's a 20 puff optional and C out, 2 of them. So each one of these is going to have 1, 2, 3, 4, 5, 6. So 6 capacitors. But 2 by 10 microfarad. Okay. So let's check something real quick. Search entry was 0.1 microfarad. Let's go ahead and get rid of that. And we have capacitance values. Hey, nice. 10 microfarad. Apply. Would you look at that? Again, X5R. The thing kept telling us that that's absolutely good. So X5R, 0805, 10 volt. These are the output capacitors. So we need to go a little higher because we're going to have one of these that's going to be a 16 volt output, or higher than that. So let's go to 25 plus, apply filters, because you always want to rate your capacitors at least twice what you're putting through them, only because, you know, they'll last longer. It's not as much of an issue with the ceramic ones. You can be much closer, but still, nobody's complaining at that cheap per. I mean, 6 cents. Alright, so that's going to work. And again, they are cheap as get out. So we're going to go ahead and copy, paste. So these are our capacitors, and we'll be putting them into the schematic in just a minute. So we're going to go ahead and have those. So 1, 2, 1, 2, 1, 2. Wire, I want you. Value. So this is going to be a mouthful, and that makes a mess of things. So what we're going to do is value. And we're just populating everything. I remember how to do a thing. And that's why you don't want to have your lines on the wrong layer, because then they're not actually connecting anything. Okay, so we wanted you back up. And the capacitor goes on this side. So this guy, there we go. See, now it's connected. Now we are being smart. And this goes to SW, so let's go ahead and do it this way. And for ease of readability, anytime you have more than points crossing or anything like that, you want to go ahead and put the dots down. If the line terminates there, it's easy enough to see, but whenever you have something going across, a lot of times you can have lines going through lines. And unless there's the little dot there, you don't know if they're connected or not. And if they're not supposed to be connected, it's always a good idea to use the move tool and just try to grab it. And if it pivots on your dot, you know that you're good. Alright, and then the output is on the other side of this guy, goes to these. Oop, can't place a junction on a junction because I had the wrong tool. Goodness. Alright. Now we need an inductor. 15 and 22 microhenry, and then further down. Oh, these are all the different, so 12 volt out, and then L is just like, okay, whatever. It's actually giving me all the part numbers and everything. What I want is this table. So with a V out of 12, we want 56 microhenry. So 15, 22, and 56. Microhenry. Fixed inductor. Alright, now for this part it said 0.8 output current at 12 volts. So let's go ahead and let's overbuild this a bit. Because if I put something on there that's going to give you an amp, I bet somebody will want to use it. 800 milliamps. That's saturation. What am I doing? There we go. There is one part. It's good enough. And no real good price breaks. Alright, so we're using this guy. He is a surface mount power inductor. So let's go ahead and manufacturer part number. Save as. There we go. Let's make sure we get a data sheet for him too. Perfect. And now the one that we pulled up, 56 microhenries. are we going to get lucky? And it's going to be exactly one part size. So, here comes the fun part. Inductors, a lot of times, don't have standard footprints. They are the size that they need to be. So we are going to have to build the recommended layout footprint so that we could solder this. So fun. This will be fun. So let's go to the library. Do that later. Let's do the footprint first. Let's just get this over with. So this says 6.7 by 6.7. Alright, so the first thing is that this fun little buddy, come on, break out. Thank you. Here we go. Has a funny looking footprint. So let's get this taken care of. So the first part of the footprint is that there is a 3.00 radius. So let's go ahead and build that first. And of course it's going to be that way, so we're going to go to millimeters, and this is going to be 0.1. 0.05. Okay. Properties. The radius of this, oh, I was almost dead on, 3. And then its position is going to be 0, 0. Ding, we're centered. So now we're going to build the pad around this circle. I need to start at the center point here. There we go. There. No, I'm not going to do that way. So this is 2.4 from there to there, which means it's 1.2 on center line. So easy enough to do this. Clip the end. Okay. So don't care, but minus 1.2, 0.2. That gives us our line to build off of. 1.2, 1.2. So that gives us where we're going to go ahead and build our pad. So 7.3, so 2.4, 2.4, and 2.4. Alrighty then. So half that would be 2.4 and 1.2, so 3.6. And then we make a polygon in here. That's going to be our actual pad. Since we're going to make it a surface mount device, we are also going to have to put in what they call the paste layer, and we're also going to put in a solder mask keep out. So we're not just going to be putting the copper on here. We're going to have to put a couple other layers so that this comes out well enough in our design. And this is supposed to be 7.3 wide, not 7.2. So we're going to go ahead and add a 0.5 and a 0.5, and that made it the wrong direction. This one. There we go. Alright, and now we can go ahead and this is going to be on the top layer. Screw it. Freeform. I'm trying to remember how to do this. We are going to cheat. Oh, I didn't want to do it that way. Oops. We're going to get rid of you first. There we go. Properties, and he is pin 2. Perfect. And you are pin 1, and we're just going to... So the thermals, stop, and cream, we're going to get rid of them, because we don't want the program to generate those, because it's going to screw up our nice little pads here. So properties, doink, 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 apply. So now what we're going to do is we are going to paste the same guy we had before. We're going to delete that pad that was there. And then we are going to select Move Group. Properties, and we're going to move him to the stop layer. And we are going to turn on the stop and the cream layer so you can see that. So now what we've done is we've taken that pad and we've also turned it into our solder mask keep out. So we won't solder mask this actual thing. So we're going to go ahead and paste him again. Delete that. Select. We're going to go ahead and copy him. And then now he's on our buffer so that when we paste it, we've only got this. Yay. And we're going to do the same thing. Properties. And we're going to put him on the stop layer, which is our solder mask. And again, move group. Place him over top. That one can be improved. I'm not sure how here. Let's just... There we go. Let's go ahead and do this right. So let's move group, properties, stop, apply. Match it up. Paste. Properties, stop, apply, group. How about we grab the other group? There we go. And there we go. Now for the cream layer is what they call it here, and that's the solder paste layer. So if you're going to go ahead and have your design done for large production run, you're going to need what's called a paste layer. So that paste layer is what they're going to use to make a stencil that will go ahead and actually put the solder on the board with a squeegee printer, similar to if you've ever done screen printing on t-shirts or something like that. So in order to do that correctly, we need to make sure that we go ahead and put some more of these on. But we're not going to want to put as much paste as this guy will put on there, so we need to make it smaller. So we're going to go ahead and look at his data sheet and see if there is a paste fit. And no, we've got how are they in the tape carrier, how are they in that, so no. Alright, so good rule of thumb is shrink it. And there's not going to be any so let's go ahead and select him. Properties. Layer is going to be top cream. Apply. We are going to copy group and then set him up there, and yeah, I'm good with that, because it doesn't have to be perfect. I want to move group. There we go. Alright, so now we've actually built up our pads. So now the other thing we need to do is that this component has a little notch to the device. We don't care about that. It's actually a non-directional part. What we do need is he needs a name that is spelt correctly. So he needs a name. It needs to be on the names. There we go. He needs a value. And now we need to set the dimensions, or placement, sorry. almost forgot about you. There we go. Alright. And how do we set this? How big are you? He is 6.7 by 6.7 square. Want to make sure we've got a decent amount of keep out around him, so 7.3, so that's fine. So we'll go ahead and give him and there. We have our footprint for our surface mount inductor. And it only took us 3 hours. No, it didn't. And save. And now we're going to go ahead and new symbol for inductor. Not you. Not in the packages. Go. Oh, previous, that might work. Hey, there we go. Ah, we can steal this one. You. Open in the library. Symbol. Okay. There we go. There we go. Copy group. Paste. Save. Component. Inductor. And we're going to have inductor. New. This is this guy. So we're going to go ahead and value prefix L. And pin 1 to pin 1, pin 2 to pin 2. Inductors, ceramic capacitors, and resistors are very easy parts to connect because you can't get them backwards 90% of the time. Alright, and let's save this. And we'll put you to sleep. Go back to here. And we'll go ahead and connect this. So we now have inductors. Okay. So this inductor on SR, that guy. And this was the 56 microhenry. So he goes from there. There we go. excuse me, value. $56 microhenry. Good enough. And those guys are bypassed to ground. And I think that's good for now. Let's go ahead and save this. And I hope either you found this incredibly boring, but were too lazy to turn it off, or you found this interesting, and I will keep going more next week. I'm going to go ahead and try again at 4 p.m. Pacific time. So, see you next Saturday.